Welcome to some current electricity basics. We're going to get started here by talking about three electrical variables: resistance, voltage, and current. We'll start with resistance. Resistance is the opposition to the flow of electrons. Resistance is controlled by a number of variables. And we're going to take a look at this first. We can find this equation on the reference table that controls the various variables that control resistance, and we go and we look that up and we discover that resistance is rho L over A. So here we see three variables that control resistance. There's actually four. There's a fourth variable hidden in one of those variables, and we'll talk about that. And the unit of resistance is ohms, so we'll add that. And the symbol for ohm is the Greek letter lowercase omega, often referred to as an upside down horseshoe. All right, back to the variables that control resistance. Rho, which you know earlier in our discussion of fluid mechanics, is a symbol for density, but in electricity, rho is a symbol for resistivity. Resistivity is a characteristic of a material that depends on its atomic composition. So by the nature of their composition, atomic composition, some materials resist the flow of electrons more than others. We call materials with low resistivity conductors, and we call materials with high resistivity, we would tend to say that they are insulators. Materials that have very low resistivity would be materials like silver, gold, copper, aluminum, all of which have been used as conductors. Materials with very high resistivity would be things like wood, glass, and plastic, materials that resist the flow of electrons greatly. As you can see by the equation, that resistivity and resistance have a direct relationship. Don't confuse resistance to be the same as resistivity. Resistance depends on a number of factors, whereas resistivity is simply dependent on the atomic structure of the material itself. If we were to go and look up values for resistivity, we would see hidden within resistivity is a fourth fourth variable that contributes to resistivity, and that's temperature. If we were to go and look up resistivity, we would see that our resistivities would be qualified to be at a certain temperature. For example, if we go to the New York State reference table in the Regions course, we see that the resistivities are all at 20 degrees Celsius, which we know, of course, is room temperature. So why does temperature impact resistivity and therefore impact resistance? Well, as you learned in the thermodynamics unit, temperature is a measure of the average kinetic energy of the molecules. And so as the temperature increases, that indicates that the average kinetic energy of the molecules is also increasing. And when we're talking about a solid, what that simply means is that the atoms vibrate more. So you can imagine if you're an electron trying to get from one end of the conductor to the other. Here's your electron trying to get from this end of this wire to the other end. That if the atoms were vibrating faster, it would make it more difficult to get from one end to the other. So again, temperature also has a direct relationship to resistance. As temperature increases, resistance increases, and in reality what's happening there is as temperature increases, resistivity increases, which therefore causes resistance to increase. You may, in your course of your life, heard of superconductors, for example. And then superconductors tend to be cooled at a very low temperature, and a substance like liquid nitrogen, for example, and those substances would have very low resistance because their atoms are vibrating very slowly. Of course, the perfection would be to have your conductor at absolute zero. The atoms would not be vibrating at all, and that would be your perfect conductor, and depending on the material. All right, so we're going to move on to length, and we'll label our conductor here with its length. And clearly here, what we see is that as length increases, the resistance of the conductor increases. And why is this? To understand this, it would be helpful if we kind of zeroed in on the conductor itself. And what we're going to do is we're going to take and we'll let these circles be atoms. We'll let our material here be copper. And so if the circles each represent atoms of copper, we're zeroing in on the substance itself. We'll give ourselves just a few to work with here. What would be helpful to understand is how does the electron get from one end of the conductor to the other to flow in the first place? And there's a couple conditions that need to be met, which we will discuss. Okay, but what happens here is in order to get for the electron to get from one end of the conductor to the other, okay, it has to negotiate a path between the atoms of the material to get from one end of the conductor to the other. So what happens here is that if you increase the length of the conductor, what you're doing is you're putting more atoms in the electron's path to get from one end to the other. So from this logic, it should make sense to us that as length increases, resistance also increases. Our last factor that we're going to take a look at is cross-sectional area. Which in this case, the cross-sectional area of our conductor is a circle. And AP does like this kind of a question, and we'll talk more about that in a moment. But as we can see from the equation, apparently, that the relationship between cross-sectional area and resistance is inverse. What that means is as cross-sectional area increases, that the resistance decreases. The electricity term for cross-sectional area is gauge. And some of you familiar with guns, etc., gauge is done by number, and the lower the number, the larger the diameter. So for example, a 12 gauge wire would have a larger cross-sectional area than a 14 gauge wire that you would use to wire your house, for example. Now, why? Why is cross-sectional area inversely related to resistance? That kind of doesn't make sense based on our previous discussion with length. It would make sense to us that as the cross-sectional area increases, that you're, again, putting more atoms in the path for the electron. But in reality, what's happening here is by increasing the cross-sectional area, you can see if we were to do that, that you would be adding more paths for the electrons to be able to flow. So that's why that that's why that decreases resistance. Okay, and again, a heads up here that a question that they like to ask is if we change the radius by a certain factor, what would happen to the resistance? Be careful with that question, because since your cross-sectional area is a circle, the area would be calculated by pi r squared. So whatever factor by which you change the radius, you have to square that, and that's the factor by which the resistance is impacted inversely. Okay? I think that'll do it for the variables that control resistance, the opposition of flow of electrons. Let's move to voltage, which we've already had some discussion on our unit in electrostatics. Voltage is the work done per unit charge to push electrons through a circuit if you think about, often used as the water analogy in current electricity, if you think about water moving through a hose, for example, voltage would be similar to the water pressure that's pushing the water through the hose. And as we discussed earlier, our units of voltage is volts, and the symbol of which is capital V. Current we've already had a discussion with as well in our previous unit. Current is the rate of charge flow in a circuit, similar to the flow rate of water in our water analogy. So it's the rate at which the water would be moving through the hose, so to speak. And current, the equation for that is I equals Q over T, rate of charge flow, and the unit of current is amperes, symbol of which is simply capital A. You'll also hear that often abbreviated amps. Okay, we're going to move on and talk about Ohm's law. Ohm's law is simply a relationship between those three electrical variables that we just got done discussing. And if we started with a graph of voltage versus current, if the conductor is ohmic, in other words, it obeys Ohm's law, what we see is that we get a linear fit to the data between voltage and current. This, of course, indicates that voltage has a direct relationship to current. We've been down this road many times in this course. How do we get from saying that V is directly proportional to I to saying that V is equal to I? Well, that, of course, as you're used to, happens by getting a proportionality constant that comes from the slope of our graph. And what was discovered is that the slope of the graph is equal to the resistance of the conductor itself, which would, of course, be able to be calculated by the equations we discussed earlier. So R becomes the proportionality constant for voltage and current, and hence we get what is called Ohm's law. There are several variations of Ohm's law. You can go V equals I times R, or R equals V over I, or if you wanted to solve it for current, of course, that would be V over R. I like to tell a interesting story. It has three characters in it. That is a vulture, an Indian, and a rabbit. And in that story, all you have to remember is what each character sees with the perspective of the other. The vulture, from his point in the story, sees an Indian next to a rabbit. The rabbit would see the vulture or the Indian, and the Indian would see the vulture or the rabbit. If you remember that cute little story, what that does is it gives you a way to remember how to calculate any of the electrical variables using Ohm's law. I've also seen this kind of analogy used as well. If you take a circle and you divide it in half horizontally, and then the bottom part you divide vertically, if you take and put the V in the top part and the I and the R in the two bottom parts, if you cover up the one that you're looking for, then that variable is the relationship of the other two variables. So in other words, if we cover up V in this circle, V is equal to I times R. If you cover up I is V over R. If you cover up R, R is equal to V over I. Okay, so you could use any of that. All right, so we're going to call this Current Electricity Basics Part 1. And thanks for listening, and come back for Current Electricity Basics Part 2.